Myself Ankita. Today I am going to prepare an audio recording for visually impaired student on the topic hard and soft acids and bases from Pardeep Inorganic Chemistry Volume 3rd by Dr. K. Bhasin. Hard and soft acids and bases. The term hard and bases are routinely used in our daily life. Chemists have been classified substances as acids and bases since long time. Lavoisier noted that the commonly element in all acids was oxygen. The word oxygen in Greek means odd acid former. However, showed later that all acids contain hydrogen. It was in 1884 Arrhenius developed the theory of acids and bases, known today popularly as Arrhenius theory of acids and base. According to Arrhenius, an acid is a substance which gives hydrogen ion H positive ion in aqueous solution, and base is a substance which gives hydroxyl ions OH negative ions in aqueous solution. The strength of an acid and a base depend upon its capacity to provide H positive and OH negative ion respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative ions give the reaction H2O. In 1923, Jane Bronsted and Lowry independently proposed a acid-base theory. According to this theory, an acid is a proton donor and a base is a proton acceptor. The acid-base reaction is regarded as a proton transfer reaction. Lewis gave another journal definition of acid-base behavior in terms of electron pair donor and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, whereas a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor, while a base is a substance which and base is a electron pair donor. In other words, an acid is electron pair acceptor while base is a electron pair donor. The earlier definition of acid and base were based upon the observation properties such as taste, ability to dissolve substance insoluble in water, and their effect on vegetable dye. The term acid was applied to substances that have a sharp or sour taste, turn blue litmus to red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substance insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste, soapy feels, turn red litmus blue. However, tasting and feeling chemicals are dangerous method of determining whereas the substance in is an acid or a base. You should never ever taste or touching solution of chemicals in laboratory. There are, however, methods of recognizing acid and base. For example, acid and base change the color of certain dyes, known popularly as indicator. One of the common indicator is vegetable dye obtained from lichens known as litmus. Aqueous solution of acid turn the litmus red, whereas aqueous solution of bases turn it blue. Thus, any substance which has unpaired electron can act as Lewis base, whereas substance which has an empty orbitals to accommodate a pair of electrons act as a Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis base, and a substance capable of accepting a pair of electrons are regarded as Lewis acids. Acid base or neutralization reaction may thus be regarded as donor or acceptor or coordinate covalent bond formation reaction. Classical example of Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is Lewis acid and ammonia is Lewis base. NH3 Lewis base plus BF3 Lewis acid give the reaction NH3BF3. Donor acceptor or coordinate bond formation reaction. Lewis acid Lewis concept of acid and base is very commonly used because of its simplicity and ease with which the formation of coordination bond can be explained. In brief, all the usual ligand can be regarded as Lewis base, whereas all the metal ion can be regarded as Lewis acid. The degree of affinity of a metal ions for ligand can be termed as Lewis ability, and the tendency of the ligand to combine with the metal ion can be regarded as Lewis basicity. Now, next concept is hard and soft acid and bases. An acid-base reaction, according to Lewis concept, involves the reaction between a donor atom A and acceptor B as to form a complex as given below. A plus B give the reaction A B. The formation of the stable complex between the donor A and the acceptor B depend upon the nature of the species A and B involved. It has been since long time that certain ligand form more stable complex with metal ions such as Ag positive, Ag2 positive, Pd2 positive, Pt2 positive. On the other hand, certain ligands form stable complex with metal ions such as Al3 positive, CO3 positive, Pt4 positive. Based upon the preference bonding, the acid and base have been classified into two groups, that is class A and class B according to their preference. Class A metal ion include all alkali metals, alkaline earth metals, lighter or more highly charged ions, for example Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive, hydrogen ion H positive. Class B metal ion include heavier transition metal of second and third transition series like CD2 positive, Hg2 positive, Pd2 positive, Pt2 positive. Heavier transition metal in lower oxidation state. Example Ag positive, Hg2 positive, Cu positive. Low valent metal ions such as zero valent metals in metal carbonyls. Depending upon the type of metals, ions ligand can also be classified as class A and class B depending upon their preference. Class A ligands include molecules or ions with donor atom nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that class A ligand prefers to form strong complex with class A metal. Class B ligand includes molecules or ions with donor atom phosphorus, arsenic, sulfur, selenium, iodide, etc. Class B ligand prefers to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acids and base for class A and class B metal ions and ligand respectively. Accordingly, class A metal ions are referred to hard acid while class B metal ions are called soft acids. Similarly, class A ligands are named as hard bases whereas class B ligands are termed as soft bases. Now, classification of acids and base as hard and soft. Pearson observed that it is possible to correlate acid-base interaction on the basis of hard and soft acids and base. He observed that this A metals ions, that is acid, were small, compact and were not very polarizable, and these preferred ligand that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ions and the ligand they prefer appears to be larger in size and more polarizable. He described that acids and base as soft. Pearson generalized the acid base relationship and expressed that hard acid prefer hard bases and soft acid prefer soft bases. Classification of acids: a general classification of some common hard and soft acids along with their borderline as given below. Hard acids: H positive, Li positive, Na positive, Be2 positive, Mg2 positive, Ca2 positive, Cr2 positive, Al3 positive, Sc3 positive, Ga3 positive, Indium 3 positive, La3 positive, Cr3 positive, CO3 positive, Fe3 positive, As3 positive, Ce3 positive, Bf3, Bcl3, AlCl3, AlS3. In soft acids, Cu2 positive, Ag positive, Au positive, Hg positive, Pd2 positive, Pt2 positive, Hg2 positive, gallium iodide, BH3, gallium chloride, gallium bromide, oxygen, chlorine, bromine, iodine, nitrogen, carbenes. In borderline acids, Fe2 positive, CO2 positive, Ni2 positive, Cu2 positive, Zn2 positive, NO positive, Bi3 positive, Sb3 positive, etc. From reveals that hard acid usually have the following characteristics. Hard acids are cations of smaller size and lighter elements. Hard acids are cation of higher oxidation state. Example: Cl3 positive, Cl7 positive. Hard acid are molecules or cation with less number of valence electron. Hard acid hold the valence electron tightly and consequently are not easily polarizable. In summary, hard acid bind strong to a proton. Hard acid are small size, comparable, and are not easily polarized. A close look from tables also reveals that soft acid possesses the following characteristics. Soft acids are cations of the large size or heavier elements. Soft acids are cation of lower charge. Soft acids are molecules with large number of valence electrons. Soft acids do not hold the valence electron tightly and are therefore easily polarizable. Soft acid does not hold the valence electron tightly and therefore easily polarizable. In summary, soft acids are large size and easily polarizable that bind strongly to the high polarizable ion. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are neither too hard neither too soft acids. Such type of acid that are neither hard nor soft are called borderline acids, which are shown on the extremely right of the table. Borderline acids have property which are intermediate between that of a hard acid and a hard base. In case of borderline acids, the properties such as size, oxidation state, and polarizability of the cations molecules are neither too low nor too high. On the other hand, soft acid will opposite trend and the following order of preference for binding the donor atom within the group: I negative greater than Br negative greater than Cl negative greater than F negative. In the similar way, R2Te greater than R2Sc greater than R2S greater than R2O. In the similar way, R3Sb greater than R3As greater than R3P greater than R3N. Now questions: which type of interaction do you accept between a hard acid and a hard base? Answer is: since both hard acid and hard base are not easily polarizable, their interaction are ionic. Second question is: which type of interaction do you accept between a soft acid and a soft base? Since both soft acid and soft base are usually polarizable. The interaction between them are predominantly covalent. Now, classification of bases. A general classification of some commonly used ligand into hard and soft along with the borderline bases are example of hard bases: fluorine negative, chlorine negative, NS3, RNS2, N2H2, H4, ROH, H2O, OH negative, O2, 2 negative, SO4 2 negative, PO4 3 negative, CH3 CO negative, ClO4 negative, NO3 negative. Soft bases are H negative, R negative, I negative, C2H4, C6H6, RSH, RH2S, RS negative, Cn negative, SCN negative, S2O32 negative, etc. Borderline bases are Br negative, C5H5, N, C6H5, NH2, N2, N3 negative, NO2 negative, SO32 negative, CO, R and C. A glance from the tables reveals some of the important characteristics of hard bases. Hard bases bind strongly to the protons. Hard bases contain donor atom of high electronegativity. Donor atom is hard bases possesses low polarizability. Hard bases are not easily oxidized. Hard bases contains empty orbital of high energy. In summary, hard bases bind strongly to a proton donor atom. In case of hard bases is of high electronegativity and low polarizability. A further inspection from tables reveals that the following features are observed in case of soft bases. First one is soft bases contain donor atom of low polarizability. Soft bases contains donor atom of low electronegativity and high polarizability. Soft acid get easily oxidized. Soft acid are associated with empty low lying energy orbitals. In brief, soft acid contain less electronegative non-metal includes carbon, sulfur, phosphorus and iodine. Donor atom in such bases possesses donor atoms that are easily polarized. Just as there are borderline acids, there are borderline bases also. The property of borderline bases are in between those of the soft and hard bases. It is important to note that categories are not rigidly divided. For example, the halide ions form a series from the very hard fluoride ion through the hard borderline chloride ions to the borderline bromide ions and the soft iodide ions. The soft acid, also known as class B metal ions, and the group of the metal ions that are in the lower right position of the metallic elements. Now, Pearson HSAB principle. Pearson proposed a simple rule for predicting the stability of coordination compound formed between acids and base. This rule is quite often named as HSAB principle. According to Pearson HSAB principle, hard acid prefers to bond with hard bases while soft acid prefers to bond with soft bases. It is important to note that hardness and softness of acids and bases refers only to hard and soft interaction. It is by no means related to the strength of acids and bases. For example, both F negative and OH negative ions are hard bases, but the basic strength of OH negative ion is 10 raised to power 13 times that of F negative ions. In other words, hard acid will show the following order of preference of binding the donor atom ions with a group: F negative ions greater than Cl negative ions, greater than Br negative, greater than I negative. In the similar way, R2O greater than R2S greater than R2SE greater than R2TE, R3N greater than R3N greater than R3AS greater than R3SB. Now, application of HSAB principle. Pearson principle of HSAB has a number of applications in inorganic chemistry. Some of these are discussed below. First one is stability of the complex. We have already noted that hardness and softness of an acid and bases are related only to hard and soft interaction. Hardness and softness of acids and bases has nothing to do with the inherent acids and acidic and basic strength of acids and bases. For example, both OH negative and F negative ions are hard bases, although OH negative is for stronger as a base and than F negative ions. In fact, OH negative ion is 10 raised to power 13 times more stronger a base than F negative ions. However, in HSAB principle, both OH negative and F negative ion are at par with each other. Pearson in 1963 explained the relative stability of coordination complexes on the basis of HSAB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. A Lewis acid plus B Lewis base give the reaction AB complex. The complex will be more stable if A and B are either both hard or both soft. The complex AB will be less stable if A is hard, B is soft, or A is soft, B is hard. For example, a complex between a soft acid Ag positive and a soft base I negative ion is quite stable in contrast to the one between the soft acid Ag positive and hard acid F negative. Ag positive soft acid plus 2 I negative soft bases give the reaction AgI2 negative stable complex due to soft interaction. Ag positive soft acid plus 2 Fi negative soft hard bases give the reaction AgF2 negative unstable complex due to hard soft interaction. Similarly, the reaction between LiF and CSF resulting in the formation of LiF and CSI constitute an interesting example suggesting the stability of soft and hard combination. LiF hard soft plus CSF soft hard give the reaction LiF hard plus CSI soft. Some of the other important reactions suggesting the stability of the soft and hard interaction are given below. CuI2 hard soft plus CuF soft hard give the reaction CuF2 hard plus 2CuI soft. Another reaction is CaFS hard soft plus H2O hard give the reaction CaO hard plus H2S soft. Another reaction is BeI2 hard soft plus HgF2 soft hard give the reaction BeF2 hard plus HgI2 soft. The rule of thumb in determining the stability of the complex is the formation of hard and soft interaction. Now a question is why COF6 3 negative complex is more stable than COI6 3 negative. Answer: in both the complexes COF6 3 negative and COI6 3 negative, the oxidation state of cobalt is +3. CO3 positive is a hard acid. Therefore, its combination with a hard base, that is F negative, will lead to COF6 3 negative, which is hard interaction. On the other hand, combination of CO3 positive with a soft base I negative will lead to COI 3 which is hard soft interaction. So COF 3 is more stable than COI 3. Now classification of acids and bases. The acid and bases can be classified as hard or soft depending upon their preference for hard and soft reaction. Let us consider the following reaction. BH positive plus CH3Hg positive give the reaction CH3Hg B positive plus H positive. We already know that H positive is a hard acid, whereas CH3Hg positive is a soft acid. If B happens to be hard base like NH3, the reaction on the left side will be preferred. NH4 positive plus CH3Hg positive give the reaction CH3H positive plus NH3 plus H positive. Conceptually, ammonium can be written as NH4 positive co NH3 positive hard base plus H positive, which means the formation of NH4 positive is preferred because the hard acids H positive and a hard base NH3. On the other hand, if B is soft base like R2S, the right hand side reaction will be favored. R2SH positive plus CH3Hg positive give the reaction CH3Hg SR2 plus H positive. Conceptually, CH3Hg SR2 positive can be written as CH3H positive soft acid plus SR2 soft base, which means the formation of CH3HgSr2 is preferred because of soft acid CH3Hg positive and a soft base Sr2. Similarly, an acid A can be classified as hard or soft depending upon the direction of equilibrium. AF plus SCN negative give the reaction ASCN plus F negative. We know that F negative is a hard base and SCN negative is a soft base. If A is a hard acid like Ag positive ions, then the above reaction in the forward direction is favored. AgF plus SCN negative give the reaction AgSCN soft plus F negative hard. Conceptually, AgSCN is formed through soft interaction. Hence, according to HSAB principle, the reaction is favored in the forward direction. On the other hand, if A happens to be hard acid, then the forward reaction is not favored, rather the backward reaction is favored. Now, OH negative is stronger base than SO3 negative and hence cannot be replaced by the weaker base SO3 negative. This reaction, however, is favored by HSAB principle. CH3CdOH soft plus SO3 negative give the reaction CH3Cd SO3 negative plus OH negative. It is important to conclude at this stage that Lewis base reaction are governed by two independent principles. First one is strength of acid or base. Second one is softness and hardness of acids or base. The definition of hardness primarily used the idea of polarizability, which states that a less polarizable species is harder than and a more easily polarized is soft. For ions of similar charge, the ratio of charge to radius should be used to assess the relative polarizability or relative hardness or softness. However, HSAB principle does not take into consideration the qualitative idea of relative hardness and softness of the species. In summary, the major limitation of HSAB principle are HSAB principle is too general and without any qualitative scale of measurement. HSAB principle does not take into consideration the acidic or basic character of the compound. HSAB principle fails to explain the feasibility of reaction. Reaction is CH3 positive plus H2 give the reaction CH4 positive plus H positive. Here delta H is 86 kilocalorie per mole. In spite of the soft CH3 positive H negative interaction, it is probably the greater acidity of proton H positive related to CH3 cations that is responsible for unfavorable reaction. Now, limitation of HSAB principle. The hardness and softness of an acid or a base is primarily related to stability of the hard and soft interaction. It has no concern with the acidity or basicity of acid or bases. For example, OH negative and F negative are well known hard and base. However, the basicity of hydroxide ion OH negative is very large as compared to fluoride ion. In fact, the basicity of hydroxide ion is 10 raised to power 13 times that of the fluoride ions. A strong acid or a strong base is well known to displace a weak acid or a weak base. For example, the reaction between a sulfide ion and hydrogen fluoride proceed in the forward reaction. It means that strong base SO3 negative can easily displace the weaker base F negative ion from the acid hydrogen fluoride. Reaction is SO3 negative plus HF give the reaction HSO3 negative plus F negative. K equilibrium value is 10 raised to power 4. However, the above reaction is not favored according to HSAB principle as detailed below. SO3 negative is soft base plus HF is hard acid hard base. Give the reaction HSO3 negative hard soft interaction plus F negative hard base, which only favored hard and soft interaction. Similarly, a very strong base OH negative can displace a weak base from a soft acid methyl mercury to cations. OH negative hard base plus CH3HgSO3 negative soft give the reaction CH3HgOH soft hard plus SO3 negative soft base. K equilibrium value is 10. However, the above reaction is also not favored according to HSAB principle, which only favor hard or soft interaction. In both the above reaction, it is inherent strength of the bases SO3 negative greater than F negative and OH negative greater than SO3 negative that force the reaction in the forward direction in spite of less preferred formation of hard soft pair in the product. This is true in case especially when the inherent strength of bases or acid being compared to significant different. The order of basic strength being OH negative 15.7 greater than SO3 negative 6.8 greater than F negative 2.85. In other words, significant different basic strength force of reaction above reaction against the basis of hard soft interaction. However, when both the strength of acid and bases and hardness and softness are not significantly different, then HSAB principle works well, resulting in product having hard and soft interaction. For example, CH3Hg positive F negative soft hard plus H positive SO3 negative hard soft give the reaction CH3Hg positive SO3 negative plus H positive F negative hard. CH3Hg positive OH negative soft hard plus H positive SO3 negative hard soft give the reaction CH3Hg Hg SO3 soft plus HOH hard. K की value here 10 raised to power 7. It is important to mention that inherent strength of acids and base should not be ignored while applying HSAB principle. Now next concept is symbiosis. Hardness and softness of an acid or basic strength is not an inherent property of an atom but depend upon the substituent. Thus ammonia is hard base while pyridine is a borderline base. The acidic B3 positive ions is borderline between a hard and soft acid. Addition of three small size non-polarizable substituent like fluoride ions make it a hard Lewis acid, whereas addition of a electron donor and easily polarizable group like hydride ions make it a soft Lewis acids. The difference in the hardness and softness of BF3 and BH3 can be illustrated nicely in the following example. R2S BF3 soft hard plus R2O hard give the reaction R2O BF3 hard plus R2S. Second reaction is R2O BH3 hard soft plus R2S soft give the reaction R2S BH3 soft plus R2O hard. In 1968, Jorgens observed that hard ligands have a tendency to combine with the metal ions having hard ligands, and soft ligands have a tendency to combine with the metal ion already having soft ligand. He coined a term symbiosis for such interaction. The hard BF3 molecule prefer to combine with hard base F negative ion to form tetrafluoroborate BF4 negative, whereas soft acid BH3 prefers to combine with soft base H negative ions to give tetrahydroborate BH4 negative. Reaction is BF3 hard acid plus F negative hard base give the reaction BF4 negative. Another reaction is B2H6 soft acid plus 2H negative soft base give the reaction 2BH4 negative. An important outcome of symbiosis is that symmetrical substituent compounds are formed in preference of unsymmetrical substituted compound. For example, compounds containing mixed substituent interact strongly to yield symmetrical compound with the same substituent as given below. BH3F negative and plus BF3H negative give the reaction BH4 negative plus BF4 negative. Similarly, mixed fluorinated methanes react to give symmetrical methanes. CH3F soft hard plus CF3H soft hard soft give the reaction CH4 soft plus CF4 hard. In brief, symbiosis may be defined as the tendency of soft ligand to combine with a metal ion already having soft ligand and the tendency of hard ligand to combine with a metal ions already having a hard ligand. Now next concept is theoretical basis of hardness and softness HSAB principle. A number of theories have been proposed to explain the preference of hard acid toward hard bases and soft acid toward bases. First theory is electrostatic interaction theory. According to this theory, hard acid and hard base form purely ionic compound. Therefore, hard interaction are purely ionic or electrostatic. Most of the hard acids such as Li positive, Na positive, K positive, etc. and hard bases such as O2 negative, F negative and OH negative etc. are well known to form ionic compound. We know that the electrostatic energy of an ion pair is inversely proportional to the internuclear distance. It means the smaller the ion, smaller will be the internuclear distance, hence greater will be the electrostatic energy between the ions. As a result, final product formed by hard acid and hard base will be highly soluble. Now next theory is polarizing power and polarizability. In this theory, electrostatic interaction cannot explain the soft interaction because of the bigger size of soft ions. Therefore, the interaction between large size acid and base must involve covalent character. For example, soft acids such as Ag positive, Hg positive, Cu positive, etc. form strong compounds with soft bases like S2 negative and I negative, etc., which have covalent character. Almost all the soft acids have 6 or more d electrons. Soft acid with d10 electron configuration are excellent soft acids. Example Ag positive, Hg2 positive. It is these d electrons that have more polarizing power. Secondly, the soft bases like S2 negative and I negative are easily polarizable. Thus, bonding between soft acid and soft base is largely covalent. Next theory is natural occurrence of ore and mineral. Natural occurrence of ore of certain metal can be easily explained on the basis of HSAB principle. Hard acid metals ions such as Mg2 positive, Ca2 positive, Al3 positive, Fe3 positive, Cr3 positive, easily etc. frequently occurs as their oxide, fluoride, chloride, and carbonates. This is primarily due to their preferred hard acid hard base interaction. We know that oxide O2 negative, halides F negative or Cl negative, and carbonates CO3 2 negative all are hard bases. These hard acids metal ions cannot occur as sulfides S2 negative because S2 negative is a soft base and cannot form stable compound. On the other hand, soft metal ions such as Cu positive, Ag positive, Cd2 positive, Hg2 positive, Pd2 positive, etc. occur variably in ore as their sulfide due to soft acid soft base interaction. Now, the borderline acids like CO2 positive, Ni2 positive, Pb2 positive, Zn2 positive can occur both as sulfide as well as their oxide or carbonates as a result of their intermediate character. Now, next theory is catalytic poisoning. All metal atom in zero oxidation state are soft acid. Some of the metals named chromium, nickel, platinum, palladium, vanadium, molybdenum, etc. are well-known catalysts. These metal catalysts have been formed to be easily poisoned by the soft bases. Example CO, carbon monoxide, unsaturated hydrocarbons, olefins, alkynes, dienes, and arenes, organophosgenes, etc. This poisoning is attributed to due to soft acid and soft base interaction between the metal atom and the soft ligands. In fact, these soft ligands are absorbed strongly on the surface of the metal and block the reactive site by forming metal complex. In other words, the metal atom lose their activity and are said to be poisoned. Thus, soft bases complex with the metal in atomic state will act as poisons toward metal catalyst. Now, last topic of our chapter is electronegativity and hardness. Hardness and softness are related to electronegativity. Species with high electronegativity value are assigned as greater hardness, and those with lower electronegativity value are assigned as greater softness. Electronegativity means the power of an atom in a molecule to attract electron toward itself. However, in this case, it refers to the power of an individual ion participating in a reaction. For example, lithium atom is known as highly electropositive or low electronegative metals, but the cationic species Li positive with a very high second ionization potential have a greater tendency to attract electron toward itself. As a result, Li positive is considered to be more electronegative, and hence it is hard acid. On the other hand, heavier transition metal ion in low oxidation state like Cu positive, Ag positive, Hg positive, Cd positive, etc. have relatively low second ionization potential and consequently possess a low value of electronegativity. As a result, these ions are considered as soft acid. Using the same concept of electronegativity, we can define hard and soft bases. This relationship between hardness and softness can explain several important features as to why trifluoromethyl group CF3 is uh, harder as compared to methyl group CH3. Boron trifluoride BF3 is harder compared to BH3. Borane ammonia NH3 is harder than trimethylamine CH3 3N. Trifluorophosgene PF3 is harder than phosgene PH3, which in turn is harder than trimethylphosgene. Now, Mulliken first defined electronegativity as a linear function of a partial charge delta developed on an atom according Xi is equal to A plus B delta. A is electronegativity of the atom, B is rate of change of electronegativity with charge. Electronegativity value A of the atom is similar to that of Pauling's, and B is called charge coefficient. Small hard and non-polarizable atoms have higher value of B, whereas larger soft and polarizable atoms have smaller value of B. Parr and Pearson introduced a new term called absolute hardness eta for neutral as well as charged species and correlated it with absolute electronegativity Xi. The absolute hardness eta is defined as half of the difference between the ionization enthalpy I and electron affinity A. Eta is equal to I minus A by 2. I is ionization enthalpy, A is equal to electron affinity of the species. We know that Mulliken's definition of electronegativity Xi is equal to I plus A by 2. The hardness of a base and acid A may be given as eta B. Eta B B positive species is equal to half of ionization enthalpy of B positive ions minus electron affinity of B positive ions. For eta A eta species A के लिए half of ionization enthalpy of A minus electron affinity of A. In order to understand as to why this equation the base B is represented as B positive, whereas in another equation A is represented as A. Let us consider the interaction of acid A and B to form the compound AB. A is acid, B is base. Give the compound A or B. A carry del negative charge, B carry del positive charge. In the formation of compound AB, the electrons will move from B to A, which is indicated by the partial positive and partial negative charge. Hardness of B refers to a species goes from del positive to a 1 plus del positive on ionization, while hardness of A refers to a species on ionization from del negative to a charge 1 plus del negative species. If the shift of charge del is taken as equal to 0.5, then the charge on B becomes 1 plus 0.5 is equal to 1.5, and on A becomes 1 plus minus 0.5 is equal to 0.5. Thus the charge on B changes from 0.5 to 1.5 with an average half of 0.5 plus 1.5 is equal to 1, and that on A changes from minus 0.5 to 0.5 with average half of 0.5 minus 0.5 is equal to 0. That justify the reason why species B is shown as B positive and A is neutral. This is our whole chapter. Thank you.